Right, good day. Welcome to my online class, my YouTube channel. Today we will be discussing or checking how to design a shaft in torsion. So torsion, we're just referring to twisting. So when you do this to this pen, this pen will be in the torsion. So we will make use of this formula to calculate whatever variable that we might want to know. This is torque equation. Remember, torque is just the force that tends to rotate the component, but in this case it's the force that will tend to slide, to cause the layers of this thing to slide over each other. So like here, if you apply a torque like this, we are going to see the surface of this material sliding over a certain surface there. So a torque, the impact of torque in this scenario is going to tend to slide like this, the layers of this material over each other. So in that way, that torque is going to cause what we call the shear stress. So the shear stress will be that tendency that tend to slide the surface of this material over each other. Then from there we're going to have a torque. This one stands for torque. That torque is that force, is that twisting force. Then you have to use the maximum one here. I will differentiate it with the mean torque. And then there is this one is J. This one is about the resistance. Is shapes resistance to torsion. So I'm talking about the resistance of the component due to its shape. So you can see that this component is going to have a round cross-sectional shape. This one is going to have a cross-sectional shape of this kind, something like this. And then this one is having the cross-sectional area of something like this. So this profile or shape and this one will have their own resistance. Resistance, we're talking about the resistance to torsion. Torsion, I'm talking about this twisting. So if I twist this thing like this thing that I'm having there is undergoing a deformation or the change in shape. So that change in shape is happening because of the resistance of this material. It's small. So if the resistance of the material is high, when you twist it like this thing is not going to undergo a deformation. Like this one, I'm twisting it, but there is no change in shape like before as I did to this one. So that resistance, it depends on the shape of the cross section. So that resistance due to the shape is represented by this J. So there will be the resistance due to the material, which will be represented by this G. So the material I'm talking about, It can be steel or aluminum or copper, any kind of material. It can be a tire or it can be a rubber. So as you can see, the resistance of this rubber material is low. So the stiffness or rigidity of this rubber is very low. So, and then the stiffness or rigidity of this plastic material, it's high. That's why this thing, it doesn't do this, it doesn't shear, because there is a resistance. So we are going to have two resistances, which is this J and then this one. This one is about the profile, the shape of the cross section. Then this one is about the material by itself, the type of material used. So we've got this one. This one is the radius. Actually, is the distance always from the center to the point where you will be working on, or to the point where you will be looking for, I don't know, maybe a shear stress. So if you're looking for shear stress here, then you will use the distance. This R will be the distance from here to there. If you're looking for shear stress there, then this R will be the distance from here to there. If you're looking for shear stress here, that R will be the distance from here to there. So this one is the length of your shaft in consideration from here to there, and then theta is the angle of twist. So let me just let us just check the video so that we can have a better understanding of this thing called the angle of twist.
The element is initially rectangular, but when the torque is applied, it gets distorted. Let's take a closer look. Because the bar is axis symmetric, we know that individual cross-sections will rotate but won't get distorted. So the sides CF and DE of the element will only move vertically along the lines shown here. After the torque is applied, the angles of the element are no longer 90-degree angles. This gives rise to a shear strain, which corresponds to the angle you can see here. We can calculate the shear strain by considering only the geometry of the bar in the deformation. It corresponds to this angle between AB and AB prime. We can use trigonometry to derive an equation for shear strain. For small angles, gamma will be approximately equal to the tangent of gamma, which makes it equal to the length BB prime divided by the length AB. AB is the length L of the bar. We can calculate the length BB prime by realizing that it is the arc length of a circle with a radius r, covering an angle equal to the angle of twist theta. So the shear strain is equal to the radius of the bar multiplied by the angle of twist.
Right.
So our test piece here is very much into plastic definition.
Let's consider this. This is your shaft. If you consider this plane, let's say we assume that this shaft is made from the pages like this, several lot of them. So if you combine these pages like this, they will form that as a shaft. Then what's going to happen is that we are going to twist this thing on this side. You hold it there, you twist it like this. So now if you twisted this thing like this, initially this thing was straight, then after twisting it's going to be like this. Then there will be an angle formed there. That angle will give you the strain energy. Okay, let's go back to this. This is that page. After twisting that page will move from this to this line here after twisting it, after applying that force. Now when you compare this initial point and the final point after applying the torque, there will be an angle here. There will be an angle here that will be formed here. So this angle is the one that we're going to call it the angle of twist. So that angle is very important, because if you exit this angle, the safe angle, then this shaft is going to break. Therefore, they will give you the angle and say that the angle of your shaft, it must not exceed a certain value. Therefore, when you apply torque, you must make sure that the torque that you apply there is not going to cause an angle that is going to be bigger than the given angle. So this angle of twist, you can calculate it. If you want to calculate it, you calculate it using this. From this formula here, you can, we advise you to either equate this to this or this to this. We don't advise you to equate this one and this one. Mathematically, it's fine. You can equate this and this, you will get the same answers, but according to the concept or principle wise, we are not advising you to equate this one and this one. Based on what? Based on this. If you equate this and this, you will have the shear stress, you will have the angle of twist. So both shear stress and the angle of twist, to be there, they have to be a torque. To have the shear stress in a material, we have to apply torque first. No torque, no shear stress. So to have the angle of twist as well, to develop, for angle of twist to develop, we have to apply a torque. So that's why these formulas, they have to always contain this part of torque, because torque is the one that is going to induce or cause the shear stress and the angle of twist. So without torque, we won't have that. Therefore, let's group this. T max over J equals to G theta over L. So from here, if you make theta, which is the angle of twist, the subject of the formula, you will have T L over J G. So remember these two, I said that these are the resistances. So the torque will be trying to slide the surfaces. If you have a solid shaft, something like this, you can assume that that shaft is made by several layers, several rings like this. So these two are the resistances. So the bigger the J, which is about the resistance of the material, the smaller the angle of twist. The bigger the J, which is the resistance due to the shape of that profile in consideration, the smaller the angle of twist. So meaning that if this material is hard, then it's going to be difficult to twist it or to have the change in shape. So the same thing, if the profile of this shaft, it's having the bigger resistance, then it won't be easy for you to twist it. To twist it, you'll have to apply a very big force. Right. This one is the length, this one is the torque, meaning that the more the length, the more the angle of twist. So if your shaft is short like this, it will have less chances of having the bigger angle of twist. But if your shaft is long like this and then you twist it, that shaft at the end here is going to have the higher chances of having the bigger angle of twist. So the shorter the shaft, the shorter the angle of twist. So like this here, the angle of twist, somewhere here, it will be this size. this is the angle of twist, but somewhere here the angle of twist will be about this size, and then somewhere the angle of twist will be very small. So the angle of twist depends on the length. So the longer the component, the bigger the angle of twist. So that's what this formula is trying to tell us. Right, from there you can also group this one or equate this T max over J equals to shear stress over R. Then maybe let's make, I don't know, you can make shear stress the subject of the formula or talk, but let's talk about maybe the shear stress. Let's talk about the shear stress. Shear stress will be equals to T max multiplied by R over over J. Then that tells you that the bigger the torque, the bigger the shear stress. The more the radius, or the bigger the radius, the bigger the shear stress. Remember, the shear stress is due to the force that tends to slide this thing like this. So the force that tends to slide this thing like this over a certain area, that will be the shear stress, will result with the shear stress. So if you apply the big torque, then the more shear stress will be induced in the material. And then if you according to this formula as well, if you have a round shaft like this, we can assume that if you've got the shaft, we can assume that the shaft is made of different layers. It's just the rings of materials like this. You pack them together, they will form a shaft like that. So if you want the shear stress here, you will use the distance from here to there. If you want the shear stress there, use the distance from here to there. Therefore, according to this formula, the more the length of this, which is R, the more the shear stress. So that's why you'll have this thing, we call it the shear stress distribution. So here you will have lesser R, radius is small from here to there, then shear stress will be small. Somewhere there the shear radius is in between, then your shear stress will be this size. Here the radius is big or is biggest, then that's why the shear stress will be the biggest. The shear stress is represented by this line here. So the shear stress keep increasing as this radius increases. Right, now you can even solve the torque from here. You can say torque, you make torque the subject of the formula from here. Torque will be equals to what? Will be equals to J multiplied by shear stress over R. Then J, let's start with the solid shaft. For solid shaft, you will have pi d4 over 32 multiplied by shear stress, and then all divided by R. I don't know, you can put it there, all divided by R. R will be d divided by 2, radius is diameter divided by 2. So when you simplify from here, you will say, maybe let me not confuse you, let me just do it like this. This is divided by d over 2, but I'm going to change that divide to multiplication. Then if I change that divide to multiplication, I write the reciprocal of this d over 2, which is 2 over d. Then from there you simplify. This d will divide 1d, they will remain with 3. And then 2 over into 32 is 16. Then it will remain with pi d3 shear stress over 32. Then that is for a solid shaft. For solid, sorry, it's for solid. Then for a hollow shaft, we know that we use the same formula, J shear stress over R equals to pi d, this is this part here, over 32 multiplied by shear stress divided by R over 2, which is d over 2. Then from there you simplify, you do the same thing as here, and then you will have this pi, and then you will have d to the power 4 minus this shear stress, and then this 2 is the same thing, 2 into 32 will be 16, and then we'll have this d, which is this. Then this is for hollow shaft. Right, that is the formula for the torque, or the maximum torque. Here I've derived these formulas. Then these formulas actually, they will be given on the formula sheet, you will get them. But as long as you know this formula, this one, everything is coming from here. So let me just show you these formulas from a formula sheet. So there are these ones here. As you can see, it's this one and this one. They are just the same as those ones that I've been showing you there. Then from there, maybe you can also check the one for calculating theta. Already I've made theta the subject of the formula here. Theta equals to T max L over JG equals to, for solid shaft, you will have pi, T, L, then J is pi D4 over 32 multiplied by G. Then when you simplify this, you will have 32 TL over pi D4 G. And then from your calculator, 32 divided by pi, it's almost 10.2. Then I will say 10.2 TL over d to the power 4 G. So it's for solid shaft. And then for the hollow shaft, it will be the same thing, the very same formula, just that the difference will be here. TL pi for hollow shaft, J will be this over 32 multiplied by G. Then you will remain with 32 TL over pi d to the power 4 minus this G equals to 10.2 TL over this G. So these formulas are the ones that will be given to you from the formula sheet. Is these ones here. So but all of them, they are from this matter formula here. So as long as you understand this, as long as you know this, then there is no need to know those other ones. As long as you know how to manipulate, as long as you know mathematics, then it's fine. Right. Now we can go and try to solve a problem. Let's quickly go to this problem here. We can study this problem. From this problem, we have torque there is 120. We have N is 150 RPM. Then we have shear stress, allowable shear stress 75 MPa. Then I can say I have this formula. You can say it's formula T max equals to so on this space here you write percentage difference. Always T max will be this 1 point something. So this something here will be that percentage difference. Like in this one they said that the maximum torque differs with the mean torque by 10%. Then you'll say 1 point, then you write that 10 here, or 10, even though it's not 10, but you can say 10 or 10, you write it here, and then T mean. So if they differ by 25%, then you will have T max equals to 1 point. If they differ by 25%, you write 25 here. Then your T max will be equals to 1.25 of T mean, and so forth. Right, then here you will have 1.1 multiplied by T mean, which is 120 K. So you'll have 132 kNm as your maximum torque. So where's this thing coming from now? Okay, let me start with the friction. In friction we have static friction, and then we have dynamic friction. So this static one, it will be bigger than this dynamic one, the coefficient of friction, or static friction as force or as the coefficient of friction. All right, this thing tells you that if something is stationary like this, I don't know, maybe it's a car or whatever, So to get this thing moving, you will have to apply the bigger force, since the friction will be more. That friction will be this static one. It's always bigger. Then to set this thing in motion, we'll have to apply the big force. Then once this thing starts to move, the friction changes to dynamic friction. Then if it changes to dynamic friction, that friction, it will be less now. So now it means for you as well to keep this thing moving, then you'll have to apply a relatively smaller force compared to the force that you applied initially. You can experience this thing when you push the car or when you push the wheelbarrow. So at the beginning, to set that wheelbarrow in motion, normally you will apply the bigger force. More you will experience this more, especially if it's loaded, and then once it starts rolling, then you will feel in your hands that you are no longer applying the big force now. So it's the same thing with the torque. So if you have an object like this or shaft like this, to rotate this thing, okay, let me check this. So in real life, in engineering, we're talking about this. You will have a shaft here. This is the shaft, and then even this one is the shaft, but we can focus on this one. So this shaft is saving weight, it's a steel, saving mass, it's even connected to this. So in this is the generator. This generator will have friction, will have weight. So this shaft will have weight. So this mass and the friction there are the ones that are going to cause the resistance. So in order for you to rotate this shaft, you have to overcome that friction and then that mass inertia. Therefore, that's why now you will have the resistance. So with that resistance at the beginning, it means that you will have to apply the big torque, the big twisting force to get this thing in motion. So once this thing starts to rotate, then you will no longer need the big torque to get this thing running, to keep this thing running. So that is the difference between the maximum torque and the min torque. So maximum torque, we apply it at the beginning, which is going to be relatively big, and then once it starts to move, immediately starts to move, then to get that thing running, maybe running constantly, you will need a lesser torque. That torque is that min torque that they're talking about today. So sometimes they won't tell you the maximum torque. I mean, they won't tell you the percentage difference between the min torque and the maximum torque. Therefore, if they don't say anything about the difference between the maximum torque and the min torque, then you must assume that the maximum torque equals to the min torque. That is only if no mention about the percentage difference. So normally they will give you the difference in percentage. So if they don't say anything about min torque and maximum torque, that they are differing, then you must assume that they are equal. So sometimes this min torque, you will get it from this. The power equals to 2 pi n t over 60. So this power that we're talking about the power that you need to rotate that shaft like this. So there is the power that you need to move an object from point A to point B. but this time that the power that they're talking about the rotational power. Right, that's why we have to include N and the torque. That rotation will be caused by the torque, which is going to cause that thing to have the rotational speed there. Right, back to our problem. We already calculated the maximum torque, and now the question is looking for the diameter. So to calculate the diameter, since this thing is a solid shaft, then you come to this: T equals to pi d cubed shear stress over 16. Then from here, make d the subject of the formula, then we'll have 16t over pi shear stress. Then that means d would be equals to the cube root of 16t pi shear stress. Then from here you will have, you substitute, you will have 16 maximum torque 132 times 10 to the power 6, sorry, to the power 3, pi times 75 times 10 to the power 6. Then from there your answer will be 207.73 millimeter. Good. So in order to have the shear stress of this much, of 75, when you apply a torque of 132, you will need this diameter of 207.73. So if you use the shaft diameter of this size and then you apply this torque, the shear stress that will develop in that material will be 75. Right. Question 2. Now we're going to replace this. Remember the first from 9.1, the shaft was solid. Now on 9.2, we're going to replace this solid shaft with a hollow shaft. Right, so we got that from here 9.1, the solid shaft that we are going to use will have this size, 207.3 millimeter. So now we're going to replace this with a solid shaft, with a hollow shaft. Okay. So we're still going to apply the same torque on the shaft. We're still going to use the same material. It means that the shear stress will be the same because of that same material. The material is still the same. We don't change the material. We're still going to apply the same torque. So the only difference is that now instead of having solid shaft, we're going to use the hollow shaft. So since we're still going to apply the same torque, then you can say that torque that you applied before while we were still having solid will be equal to the torque that you will apply on this hollow shaft. And then from here, from this, as I've started with it, I've said that the torque for solid shaft will be this. Then we can replace it by this pi d cubed shear stress over 32, and then torque for hollow shaft is this one, then you can replace it by pi d4 minus this shear stress 16d. Then from there is mathematics. This pi, let's see. Yeah, something's not right here, sorry. 2 over 32 is 16. 2 into 32 is 16. It must be 16 here. Sorry, so here it will be 16. Pi divides pi, 16 divides 16. Shear stress is the same, divides shear stress. Then you will remain with d to the power 3 for solid shaft equals to d to the power 4 minus this over this. Hollow shaft, hollow shaft, hollow shaft. Remember, we're going to replace this by this. So this thing now is going to have outer diameter and the inner diameter. So which are these variables here? So now we have to find this dimension, the outer diameter and the inner diameter. Therefore, we are going to replace here. You will say that d of the solid shaft, you got it, is this one is 207.73 cubed equals to dh, we don't know, but from that question they said that d equals to 0.65 of capital D. So let me write it here. D equals to 0.65 of the outer diameter. Then we're going to replace this small d or the inner diameter by this. Where you see this small d, you put this. Then you'll have 0.65 d to the power 4 over dh. Then from here you only have one unknown, which is dh. Yeah, most of the students you will get tricked here. Normally you will say this and say 0.65. You will only square d, so which is wrong. So this thing is the same as, you must square both, 0.065 to the power 4, or not square, you must raise this to the power 4, then you must also raise this to the power 4. It's exponent laws. So most of you will do this part, which is wrong. So the right way is this one. So make sure that you are careful when it comes to that part. I'm coming. Right, so maybe I can just help you to solve this, because I know you will struggle with mathematics here. Then in the next step, okay, let me just take the long route. So this one and this one will be the like terms. This one and this one are the like terms. Then we can sum them. Then you will have 1. We've got 1 d to the power 4 here. You will have this. Then you will say 0.65 to the power 4. Then you will have 0.8, this one minus this, you will have 0.82149 d to the power 4. Then from there you will have DH, the outer diameter of the hollow shaft, will divide one of these. You remain with 3 there. Then from there you will have one unknown. You will remain with what? You will remain with 207.73 cubed equals to 0.82149 d to the power 3h. So even here, your next step should be, from here you must first divide by this 207.73 cubed. You divide both sides by 0.82149. So to get, you'll remain with this. Then from there, the cube root of this should be equals to dh. So I got this 221. So dh will be equals to 221.8 millimeter. Then from there, the small d of the hollow shaft will be equals to 0.65 d. Then you will have 0.65 multiplied by 221.8. Then you will remain with 144.17 millimeter. Right. Then from here we are done. We calculated the dimensions of this hollow shaft that we can use to replace this solid shaft. So on the next question, 9.3, calculate the percentage saving in weight. Okay, let me do this. We calculated the solid shaft. We got that the diameter is 207. The shaft size that we can use to transmit that amount of torque and then to have that 75 shear stress, we said the correct size will be this 207.73. Maybe at the same time, let me calculate the area here. How much will be the area of this? So you'll have pi d squared d 0.20773 squared over 4 0.3389 meter cubed, this one. Then from there we had what? We had the hollow shaft that we're going to replace this with. Then we found that what those dimensions, 144. We are going to use this diameter of 144.17, and this one with outer diameter of 2 to 1.8. Right. So let me start with this thing here. From let me see. I spoke about this thing here, this part. So I said that this is the formula for shear stress, and then the more the radius, the more the shear stress. Then the shear stress distribution will be like this. So as I've said before, right, what we can observe from here is that the inner material here is going to handle a relatively, or is going to experience a relatively small shear stress. Like at this point, shear stress is represented by this vertical line, it's small. Then here at the outer, and then the shear stress is big, is represented by this line. So somewhere here at the core, the shear stress is very small. Then because of that, what we normally do is that we remove this material here. Since this part, the core, is not going to assist that much when it comes to resisting of the torsion, when it comes to resisting the shear. This material here at the core is not going to contribute that much. So that material that would be here, actually I can say, is underused. So what we normally do, the material that will do more work is this part, because this part, that's where you're going to have the shear stress. That means you will need more resistance here, since too much shear stress will be here, not at the core. So what we can do, or what I can explain this thing better, I can say that we will to have an effective shaft with less material, we will take this amount of material here, get that 144. You take this material here, this one, you remove it, and then out of this material that you removed, which is this, you take not all of it, you take a certain portion of it. From this size, you take certain portion of it. Okay, let me say this. I divide this thing into two. The material that you removed here, you will have this portion, and this portion will give you this. So you take this one, you save it. You don't use it here. You remove it and then you just save it. It's not going to be part of this hollow shaft. That way you will save material. And then this one, you take it and put it here. You increase the radius, because this thing here on this surface is in that way you are increasing the resistance, and then you are helping this material, the other material, to hold to share the shear stress. So now this material here is going to have a good contribution when it comes to resisting the shear stress, because at this point, that's where you're going to have more shear stress. Then this one will be saved. Then in this way, you will find that the resistance of this solid shaft will be equals to the resistance of this hollow shaft with less material. So I removed that, and then I've added certain portion. This pencil line that you see here is this one. Then since I said that certain amount of materials, this one will not be used. This is the one that we've saved. Okay, anyway, from our calculations, you can calculate the area for this to see what I'm talking about. Let's calculate the area for this. Outer diameter 0.221.8. Inner diameter 144, in meters, 0.144 17 squared. So the area of this will be 0.0223. So as you can see, the area of this, it's big. Then this area here, it's small, 0.0338 compared to 0.022. So the amount of material that will be used here will be more compared to the amount of material that will be used here. Here we will use less material. Therefore, by using the hollow shaft, it means that you've saved material. So now we want to know that amount of saved materials in terms of the percentage. Then you can say, I'm going to take it from the basic. The weight of the solid shaft, which is what we had initially, minus the weight of this hollow shaft over the original weight, which is this one, weight of the solid shaft. And then we know that the weight equals to mg from science or whatever, gravitational force. So weight equals to mg. So we are going to replace this weight by mg minus this one as well by mg over mg. But this is the mass of the solid shaft, hollow shaft, solid shaft. So we take out g as the common factor. We will have g ms minus mh over msg. Mathematical, this one divides this, you remain with ms minus mh over ms. But as well, we know that mass equals to density multiplied by volume. We know that density equals to volume equals to area multiplied by length. So we're going to replace this mass by this. Then you will have mass of the solid shaft density area solid shaft, this minus but remember, this one is for solid shaft, this one is for hollow shaft, this is for solid shaft. Then since we've got the same material, density will be the same. You take out density as common factor to divide with this. The length will remain the same as well. The length of the hollow shaft will be the same as the length of the solid shaft. this one common factor, and then it will divide that one. Then you'll remain with area of the solid shaft minus area of the hollow shaft over area of the solid shaft multiplied by 100. I've already calculated these areas before. Then I said that area for the solid one is 0.03389 minus hollow shaft 0.0223 over 0.03389 multiplied by 100. So from your calculator, you'll get what? Hopefully you'll get 34. 34%. But here, since we had the diameters, alternatively here, before you come here, you can use the diameters here. You can say W, area for solid shaft will be pi d squared solid over 4 minus pi d squared hollow remember area for hollow will be capital D squared minus small d squared. These are the areas over 4. Remember I'm here. AS is this. Area for hollow shaft is this one. Then all divided by area of the solid shaft. Pi d squared s over 4. Then from there you take out pi over 4 as common factor, pi over 4 as common factor. Then after that, this pi over 4 will divide this. Will divide that. Then you will remain with d solid minus d hollow shaft squared minus d hollow shaft squared all over d solid shaft squared. Then you just have to substitute it there, and then let me try to squeeze it here. You will have diameter of the solid shaft 207.73 squared minus. Right, continue with substituting those diameters. The diameter of the solid shaft 207.73 squared minus the diameter of the hollow shaft, the big one, 221.14 squared minus diameter of the hollow shaft, the small one, 144.17 squared all over 207.73. you will still get 34 or 34.16. So that means that if we replace the solid shaft by the hollow shaft, we will save 34% of the weight of the original shaft.